Ah, okay. Glad you made it. Okay, well, we're recording. So after reviewing, then class is actually starting. People, please. Ahem. I shouldn't have to do that at this level. All of you, come on. So after reviewing, then we'll have you guys start in the test, and then I'll give you like 20 minutes to get going on it, or whatever we have left. What?
I'm shooting for 30.
Okay. You don't get the game of the clock though. By saying let's not review anything and have a whole class period. But it's not going. That is not going to happen. I promise you. I'll just call time when I feel like it. So don't even go there. And so I'll be able to handle all the questions on your list, and which are probably on anyone else's list or the union of those lists. Okay. For the formula sheet, I've added the formulas for the 3 iterative methods: Jacobi, Gauss-Seidel, and SOR. I will want to take a quick glance at anyone's concept map. Well, some of them I've looked at already, and chances are I'm fine with it. I'm just trying to avoid a situation where someone densely writes the whole class onto a sheet of paper. So if you did not do that, then I'll be okay with it. But so we'll handle that at the very end of class. So during the brief time that you're taking the exam today, whatever you brought with you is what you can use. Or actually, I'll be able to check that as I go around handing out a test. Since they're going to hand you each a test individually, so we'll just do it then. Okay, now, and then I will take a look at the test between today and Thursday, hand it back to you, and you'll have the whole class period on Thursday to get them done. Which, incidentally, I know that happens to be the withdrawal deadline. Sorry about that. I was trying to avoid tests, other classes' tests, and failed miserably, as I discovered. Sorry about that too. All right. Although I happen to know what? Yeah.
Yeah, we didn't know about that.
Okay. Yeah. Okay. Yes. It's her fault. Okay. I'm not going to say on YouTube who that is. Okay. So you can't either. All right. So I understand that there's a request to talk about problem 4 from the practice. Okay. All right. Those of you who have taken a class from me before that involves an in-class test, I'm sorry, I did not bring the turtle with me today. I will have a turtle on Thursday, and those of you who don't know what that's about, you'll just have to ponder until then, or ask somebody. But yes, the turtle will make an appearance eventually. All right. Now, so problem 4 on the practice, it's a fixed point iteration, and this is your function x squared minus 2x plus 2, and you're given that the fixed points happens at x star is equal to 1. So what I'm going to do is show you how in the general case, how a error analysis with fixed point iteration works, because what the question asks is, oh man, hold on a second. Okay, all right. I kind of goofed a little bit in the question, because it says, given that the fixed point occurs at x star equals 1, state the rate of convergence in the asymptotic error constant. what I really should have said was the order of convergence, not the rate of convergence. They are different things. I've made sure, I've checked just now, this is not an issue for a real exam. So I don't have to correct anything there. But okay, so order, and by order I mean linear, quadratic, superlinear, something like that. Order convergence. And then also, so in other words, the number r, the power that the error, previous error is raised to, and also the asymptotic error constant, always denoted by c. And actually that is related to the rate of convergence, because given c, the rate of convergence is minus natural log, not natural log, minus log to base 10 of c. Okay, so it's really a question asking what kind of convergence do we have here? So what you do is, for the error analysis, by Taylor expansion, you have xk plus 1 minus x star. So that's the error after k plus 1 iterations. Well, xk plus 1 is g of xk, and x star is g of x star, because it's a fixed point. So those two are interchangeable. And what you do is you do a Taylor expansion of g of xk and the center of your Taylor expansion is x star. So that's for, and then you'll just substitute that Taylor expansion in there. So first I'll write down the Taylor expansion. So g of xk is equal to g of x star plus g prime of x star, xk minus x star, and then 1/2 g double prime of x star xk minus x star squared. And I'll just go out one more term. So 1 over 3 factorial g triple prime of x star xk minus x star cubed, and so on. Additional terms that I won't bother to fill in. So if you substitute that Taylor expansion into here, the g of x stars are going to cancel. So what that means is xk plus 1 minus x star is equal to g prime of x star times xk minus x star. Here's the leading term. So in other words, this new error is equal to g prime at the fixed point times the old error. But then you have the other terms. And so 3 factorial is 6. So filling that in. Okay. So that's what you have in a general case. So the order of convergence is going to depend on whether any of these derivatives are 0. So for instance, if g prime of x star is non-zero, then this is a relationship between your error. It's a linear relationship. So you have linear convergence in that case. And this g prime, or the absolute value of it, is your c. It's your asymptotic error constant. Whereas if this is 0, you move to the next term. You have quadratic convergence. And then this, absolute value of this, 1/2 g double prime at the fixed point. That would be the asymptotic error constant. So you start checking how many of these derivatives, starting from the first one, are 0 at the fixed point. However many of them are 0 tells you the order of convergence. Now, most of the time, this is non-zero, so you get linear convergence. So that's the general case for fixed point. But once in a while, depending on the function, you might get something different. So if you look at this function, g, so g prime is going to be 2x minus 2. So g prime at x star is equal to 1. So you plug x equal 1 in here, and you get 0. So that tells you that it's going to be at least quadratic convergence, if not more. So to be sure, look at g double prime, that's just going to be 2, no matter what. So g double prime is non-zero at the fixed point. So this term in the Taylor expansion is going to go away, and this tells you the convergence. So for this function, we have quadratic convergence, so r is equal to 2, and your c is 1/2 g double prime, but g double prime is equal to 2, so it's just equal to 1 in this case. Now, when you have convergence faster than linear, it doesn't matter whether c is less than 1 or greater than 1. For linear, it has to be less than 1, but otherwise you don't care. Okay. All right. So, so take a Taylor expansion of your g to substitute into here. So that tells you, what we're trying to get is the relationship between the new error and the previous error. And that tells you if the convergence is linear or quadratic or something else. Okay. So, questions about that?
So in general, is expanding out to g triple prime enough? Or
Sorry, what?
in the Taylor expansion, is expanding out that much enough generally? Or should
The 3.
Yeah, well, generally it's going to be more than enough. But really what I would do is just go one at a time, plug in a derivative, and only if it's 0 do you bother continuing.
Okay.
Yeah, because it says, as soon as you get that first non-zero derivative, then it's, but that's it. Ever a question? What? Not up front, really, but yeah.
But you do want to see that.
I'm fine with a one derivative at a time approach. So, yeah, well, yeah. So really, if you want to boil it down, so in other words, if you really understood what I was doing here, what you'd really do is
You're taking
just take derivatives at x star.
Right.
Yeah, because those are your c's, so if you find that the fourth derivative is the first one that is non-zero, then it is fourth order or quadratic convergence. So most of the time, it's linear with that as your c. Mostly. Okay. Well, we have time. Whatever questions on anything are there? Yes.
I presume there'll be something about permutation matrix, and I presume also that you want us to show the permutation matrix and then what it does.
I don't know if I really care about permutation matrices that much.
But they're so much fun.
No, we're not. Because the goal is, mainly to solve a system. Now, so the only thing I really want to see is, do you perform the correct row interchanges? Oh. Okay. I didn't fit. What?
Can we do number? Because I would please do number 5.
Okay. I didn't realize I would elicit such terror, but.
Yeah.
Okay.
And then 6.
Okay. Well, I kind of assumed that those would be of particular interest. Well, other than that, we'll see how much time there is. Okay. Oh, what's going on? Okay. Sorry, it froze for a second, but it came back. Okay. All right. Well, what I can say is that I would not expect you to use the exact same notation that I used in writing up a solution. But what I do expect you to do is make it clear one way or another, however you choose to do that, what row operations you did. So as long as you indicate that in a way that I can follow.
Like what we're multiplying and stuff
Yeah.
to get. Okay.
Yeah, like what multiple of what row are you, and like, or if you're interchanging two rows, which rows?
Okay.
And really should be doing this anyway just to get the problem right. But what happens to the matrix at each step? So what's the result? But especially for multiple, like if it's a row swap, it's pretty easy to pick out. But as far as like multiple of one row, subtract it from another, yeah, write that down. Like, what is your multiplier? Because I did not ask for the LU decomposition. You don't have to write that down, but
You can write it down, Sue. Does that make you feel better?
yeah, you're welcome to write it down.
You go ahead and write it down.
Yeah. But yeah, I do expect you to follow the process that is described in the problem. Gaussian elimination, partial pivoting, forward and back substitution, as opposed to what's taught in certain other classes. Sorry, Caitlin. Okay. All right. Now, because of how this is done, like you're not doing an augmented matrix, you do not involve B at all at the beginning. That doesn't come into play until later on, like for forward substitution. Okay. So if I were to write out step for step what you would do is you check for pivoting in the first column, and you examine the entire first column. And the largest entry in absolute value has to go to the diagonal position. So you look at through that whole, and when it's the first column, you examine the whole column. When you move to the second column, you only look at this part, and then in this case, a 3x3 matrix, when you get to the third column, there's no pivoting to do. So you only look from the diagonal on down. So the largest entry is 4, which is row 3, column 1. So what that tells you is you swap rows 1 and 3. Now, why it's very important to write down these row swaps is that after you do these row swaps on A, you're going to do them to B later, in sequence. In fact, it'd actually be a pretty good idea. Once you figure out you got to do this to A, so it's not A, it's a permuted version of A. That's why I'm writing the P here. Okay. You can go ahead, if you want, and swap the same rows within B. And just keep track of that as you go. All right. So when you start a column, first check if any row interchanges have to be made. Make sure that the element at the top of the portion you're working with, again, from that's in the diagonal spot, is the largest. Once you do that, you eliminate entries, sub-diagonal entries, in the first column. So your multipliers, first for the second row, is going to be the entry you're trying to eliminate, which is 2, divided by the diagonal entry in that column, which is 4. So your multiplier is 1/2. So what that tells you is your operation is row 2, I'll use this notation, row 2 is equal to itself minus the multiplier times row 1. That's the way these always work. You're trying to eliminate a certain entry, so that row equals itself minus the multiplier times the row that you're using to carry out the elimination. So you're working on the first column, you're going to take a multiple of the first row. So if we take a look at that in the matrix, so first row is never going to change, aside from any swaps. And we're working on the second row. So off to the side here, I'm going to take this row and multiply it by my multiplier, so the 1/2. So it's going to give me 2, 1/2, and 5/2. And then I'm going to subtract that from a second row. So I have 2, 3, and minus 2. I'm going to subtract 2 minus 2 gives me 0. 3 minus 1/2 gives me 5/2. And then minus 2 minus 5/2 gives me minus 9/2. So that's what happens to the second row. Really don't need to perform this. You know it's going to be 0. You just put a 0 there. All right. Similarly, third row, your entry you want to eliminate. So it's the entry you want to eliminate, which is 1, divided by the diagonal entry, which is 4. So that's your multiplier. So row 3 is equal to itself minus the multiplier times row 1. So now for the third row, I'll take this row and divide by 4. So I have 1, 1/4, and 5/4. And I'll subtract from, I have 1, minus 1, and 0. So 1 minus 1 is 0. Minus 1 minus 1/4 is minus 5/4. And then 0 minus 5/4 is minus 5/4. So I realize it's a little cluttered, but it's also good enough in solution. Okay, that is a minus 5/4. Okay. All right. And the first column is done.
Bless you.
Questions about the first column?
So wait, what do you do with the 1/4?
Okay, so you always take your multiplier, and so here, since we're working in the first column, you'll multiply the first row by that multiplier, and that's what gave me this,
Okay.
and that's what you subtract.
From the third row.
Yes.
Okay.
Okay. All right. So, in general, to eliminate Aij, so the entry in row I, column J, it is always row I is equal to itself minus that entry that you're trying to eliminate over the diagonal entry in the same column times the row containing a diagonal entry. All right. Any other questions about first column? Okay. Now that the first column is done, you look at the second column. Fortunately for a 3x3, not very much to do. Okay. Okay, so you start with A, you did a row swap, then you did some row operations, that's why the M is here. You don't have to write this, I'm just explaining it's not the original A, it's A with stuff done to it. I'll call this P1 and M1, because all the work's been done in the first column. And the matrix we have at this point is 5 halves, minus 9 halves, minus 5 fourths, minus 5 fourths. So what you do is you look to see if yet another row interchange needs to happen. And the B that we've had up to this point is
-1.
Wow. Yeah. Okay, so we still have to carry that along with us. So you check this portion, only that portion of the second column, and you got to make sure that the largest entry goes to the second position. Well, that already is the largest entry because 5 half is greater than 5 fourths. So there's no row interchange needed at this point. So all you have to do now, there's one last row operation to get rid of that. So your multiplier for the entry in row 3, column 2 is the entry you're trying to get rid of over the entry, the diagonal entry from that column. So that's going to be minus 5 fourths over 5 halves. So that's going to be minus 1 half. Now keep in mind, when you're doing partial pivoting, your multipliers must always be less than or equal to 1 in absolute value. If not, you mess something up. Maybe you forgot to pivot or something. Okay, so now that means that row 3 is equal to itself minus 5 halves times row 2. So now I'll take this row and I'll multiply it by minus 1 half. So that gives me
1 half in the parentheses.
what?
1 half in the parentheses.
Oh, whoops. Yeah. Yes, the actual multiplier, minus 1 half. Okay, so multiply this row by minus 1 half, you get minus 5 fourths and 9 fourths, positive. And then that is what you subtract from here. So after swapping in row column 1, working on column 1, working on column 2. The first 2 rows will not change. This entry you know is going to be 0. The only entry that you need to really figure out is this one. So you have minus 5 fourths minus 9 fourths is minus 14 over 4. So in simplest terms, minus 7 halves. So then the matrix is done because it's reduced to upper triangular form. So really, this is your U. And then your L comes from your multipliers. Because you have to use your L for forward substitution. So the multipliers for the 2-1 entry was 1 half. And then for the 3-1 entry is 1 fourth. And then for this entry, it was minus 1 half. That's why it's important to keep track of your multipliers. Because the next thing you're going to do is forward substitution with L, followed by back substitution with U. So you need to be clear on what these matrices are. So you just fill in the multipliers in order, the order in which you use them. So first column, second column, and so forth. Okay. Well, if this were a larger matrix, you would need to fill in L as you go and possibly swap, but it turned out not to be necessary in this case. Okay.
So for you, we use X, and for L, we use Y.
Those would be results. And because now what you do is, okay. Okay. Actually, what I would suggest is for doing L, I waited until the end. Don't wait until the end. Fill in as you go. And here's a very important thing, because I can't promise that it didn't come up in a real test problem because I don't remember. It just didn't come up here. Because the only swapping we had to do was before we even started working on the first column. Let's see. If you need to swap rows in A, you swap multipliers in L also. Just the multipliers. Don't touch these. Leave that alone. Because you're always going to have ones. Oh, dang it. You're always going to have ones on the diagonal, no matter what.
So can we swap it with a 0?
What?
That negative 1/2 and the 0 above it, or we only deal with the stuff on
Well, here's an example of what could have happened. Suppose I got to here, and this entry was the larger. I had to swap rows 2 and 3. That would mean I would have to swap these two multipliers also. Yeah.
Does that also affect the entries in B?
Yeah, anytime you swap rows of A, you must swap rows of B.
So it would be negative
And
1
that's
1
why
4.
X
Yeah.
be swapped, because
Yeah.
B is the answer to
Yes.
L
Okay.
times Y.
Yeah, because what you're doing is your next step after you handle Gaussian elimination is you solve Ly is equal to PB, where P is all the row swaps that you've done during the whole process. Now you're dealing with a 3x3 matrix. So you only have to work in 2 columns. You only have to do at most 2 row swaps. And all right, so I can't hand out this exam, obviously, or this particular copy right here, since I'm writing on it. Okay. What?
I got dibs.
Okay. Jeez. Okay. I just want to check on something for a real problem that I'm giving you. So, yeah. Okay. So that's 1, 0, 0. 3. Okay. Dang it. Okay. So. Yeah. So that, unfortunately, does turn out to be important. So, yeah. Just so that you have the correct L. So you work on the 2-1 entry, put that in here. Work on the 3-1 entry, put that in here. When you get to here, if it's necessary to swap when you get to the second column, swap these two, and then go to work on this entry, and whatever multiplier you get from your last row operation, you just put that right in there.
Okay.
So the zeros and the ones stay the same.
Yes, do not touch them at all. Okay. This must be a unit lower triangular matrix. Okay. Yeah. All right. Yeah, because what happens is anytime you do a row interchange, all prior multipliers from previous columns have to follow that row interchange. So do not forget that. You can even write it on your concept map,
Wait, what?
which you're probably doing anyway.
What am I putting on my concept map?
That, anytime you do a row interchange, multipliers from prior columns have to be interchanged as well. So if you're swapping two certain rows in particular, swap those multipliers in those same rows that go with earlier columns. Otherwise, you'll have a wrong L. So in this case, you're solving. You have two simpler systems to solve now. Forward substitution to solve Ly is equal to PB. So you're solving this system 1, 1, 1, 0, 0, 0, 1 half, 1 fourth, minus 1 half, y1, y2, y3 is equal to the rearranged b. So that would be minus 1, 4, 1. So the easiest thing to do is, here's a matrix form. If you just write this out as a system of equations, because you only have 3 of them. So then you have y1 is equal to 1. So the first one is given away.
Negative.
And then you have,
Negative.
oh, sorry, negative 1. Dang it. y1 plus y2 is equal to 4. And then 1 fourth y1 minus 1 half y2 plus y3 is equal to 1. So then you just go ahead and solve. Solve for those. And then are there any questions about that process? Because it's just algebra at that point, which I know is still a risky proposition. Because it seems that algebra is the greatest weakness of all math students at any level. Well, good point. So any questions about the forward substitution bit? Okay. Now, the final step is back substitution. So ux is equal to y. Well, u is your matrix from Gaussian elimination. So that would be 4, 1, 5, 0, 5 halves, minus 9 halves, 0, 0, minus 7 halves, x1, x2, x3 is equal to the result of forward substitution, which you see from a solution is minus 1, 9 halves, and 7 halves. And I was just doing the same thing. Write out the actual system of equations. And so you could work from a bottom up. So you have minus 7 halves x3 is equal to 7 halves. 5 halves x2 minus 9 halves x3 is equal to 9 halves. And finally, 4x1 plus x2 plus 5x3 is equal to minus 1. So you just work from the bottom, and you see each variable. It's easy to isolate from the rest. Okay. notice in the practice problem, the numbers may not have been nice along the way, but they worked out nicely in the end. So make of that what you will.
Oh, answers to math problems being zeros and ones.
Too restrictive. Actually, the answer practice says 1, 0, minus 1 is from when I took this kind of class. And on a test, we had a problem just like this. And I was talking to a classmate about it. He said, I told him what I got. He said, I got 101. That's where I wrote it. Oh, I messed it up. So, but then I only made one mistake, like toward the end, and somebody only took out 2 points, and I got a higher grade than my classmate did. So, yeah. So, yes, I messed up this problem, and I turned out okay. So, in numerical analysis, maybe nothing else. All right. So, just do the best you can. Any other questions? Because I still want to talk about iterative methods. Of course, I guess you guys do. Okay. Now, for which actually that would mean that I will have talked about half the problems. What? Okay. All right. Okay, Gauss side L. All right. Okay. All right. Now, a formula that you are given for Gauss Seidel is this. So this is what you'll have to make sense of. Okay. Now, your initial guess, so x0, all zeros. Okay.
Could we write that down on the concept map? Because I think I was confused.
Which thing?
Like that.
That formula?
Yeah.
It's on the formula sheet.
Oh,
Yeah.
you giving us a formula sheet?
Yeah.
Oh, okay, well, never mind.
Oh my God, pay attention. Okay. Now, so what happens? So my first iterate is going to have these three components. So x1, x2, x3, the superscript of 1. So how you translate this into action with these particular numbers? Out front, you will always have 1 over diagonal entries. Your diagonal entries in this case, 6, 7, 5. So just go ahead and write that down first. That's what you're always going to have. 1 over your diagonal entries in order. And then some really big ass expression in parentheses. What you will always have to start your expression are the elements of B. So just go ahead and write those down. So don't even have to really think through this part of it. Not yet. Okay, so far so good. After that's where things get a little more complicated. So what's going to happen is, in each of these components, you're going to be subtracting off elements from the same row of A, so first row, second row, third row, except for the diagonal entry. You always skip the diagonal entry. So this 6, 7, and 5 that you included here, now you forget about it. You've already accounted for it over here.
Yeah.
So what you'll have is, in this case, minus 1 times, and since that's in the second column, so this is the 1, 2 entry, and then I have 0, which is a 1, 3 entry. So I'll just go ahead and write those entries down, but watch, I'm leaving space, so keep that in mind. Actually, didn't leave space over here. Okay. Second row, I'm going to have the 2, 1 entry and the 2, 3 entry. Third row, I'm going to have the 3, 1 entry and the 3, 2 entry. So everything except the diagonal is what you'll put in here. So in fact, go ahead and fill in those entries, because you're going to have this every single time. It's the other numbers that are going to change from one iteration to the next. So a 2, 1 entry would be 2, and then this one would be minus 2. Put a minus before it also. 4, and then 1. So in fact, what I would suggest maybe is, as a first step, like separately from your actual work, just go ahead and write this down. So 1 over diagonal entries here, elements of B here, off diagonal entries of A go here, in order from left to right, and in that row, and always with a minus in front. So just blast that out. Get it down on paper, because this is your template for every iteration you'll make. Any questions about it? Okay. So hopefully that made this a whole lot easier.
Yes.
Okay. Never thought of this until now, actually. Okay. Now, what you actually fill in is, because here you're starting with x0 and you're trying to make x1. So you want to separate entries that are to the, like below the diagonal versus above the diagonal. So like in the first row, everything is above the diagonal. Here it's like split. So if you separate, here are the entries below the diagonal, so I is greater than j. Here are the entries above the diagonal, where I is less than j. So go ahead, draw a line to separate, because how you treat these entries is different. So for these entries, you have to use your previous x. In this case, 0. So go ahead and fill in those entries. So this is x2, the second component, and this is the third component. Which component do you use? The column index. Always use the column index to figure out which entry you're supposed to put there. Same with this one. Here's the third entry, so we again put 0. So your old entries are what go there, because you like to use the most up-to-date entries, but these are the most up-to-date entries available. Below this line, use the new entries, because what you do is now this entry completely determined. You can actually grind this out. All you get is 1, because we had so many terms that are 0. Now this entry goes down here. So you fill in 1, because that's x1 iterate 1, because it's now available. And down here too. Okay. Now this entry, completely determined. You can go ahead and work that out, and you get 2 7s. And that goes down here, because now that entry is available. This is x2 iterate 1. And you can grind that out now and get minus 37 over 35. Okay. So now you're going to use the same setup for the next iteration, where now these become your old values that you fill in above, for the entries above a diagonal. And then as you compute elements of x superscript 2, like these guys will be filled in down here. And you'll just keep going. And you're going to see, like, do these appear to be approaching something? Right. So any questions about this process? Okay. Now, that's Gauss-Seidel. If it were Jacobi, it's actually a little easier because you would only use the old entries
Yeah.
in these positions. That's the only difference, though. So you wouldn't have to like divide, like do one thing up here, one thing down here. It's the same thing throughout. I'm not putting SOR in the test. I'll tell you that right now.
You're not putting what?
SOR.
Oh.
You mean I spent all that time, hand and paper on
Yes.
SR, just completely
So
wasted?
thank you.
Thank you.
Thank you.
Well, but you feel silly now, don't you? Okay. Are there?
Now these become the zeros.
Okay. Are there any other questions about anything on the practice test? At all?
Same exact format for Jacobi,
Yes.
except minus the division.
Right.
We just
Like
use
this-
whatever
this
X.
squiggle.
Yeah, the
Yeah.
previous tax.
Right.
Yeah, you did not looking for up-to-date
So
values.
like if we did another one though, would we still use the
We're using the
zeros?
1, 2 over 7.
Oh,
Or would we use?
You use the 37 over 35.
Yeah,
Okay,
now
so
you
we can
use
still
these.
use that for the same.
Yeah, but
Yeah.
because once you finish this iteration, then you forget about that completely.
Okay.
Yeah,
So the second. I also look like Jacobi one though.
Yeah.
So you see the same thing.
Yeah, yeah.
Yes.
Okay.
Right.
Alright.
Okay.
Let's go. Let's take this bad boy.
Alright, let's pass this out.
Pass it
Alright.
around.
Okay.
Now or never.
I'm so.
Let's go.
So yeah, something tells me that if anyone else were to ask a question, that they would get equal odds from 17 people. 15. Okay. As I come to you to give you a test, I would like to get a glimpse of your concept map. Well, okay, once up front, I've already seen them, so that's it. Well,
Yeah, you can just leave that up there.
no, I've got to retain something.
Do you want me to take this computer to Teresa and let her stop it?
Oh, what? Oh, right.
Should I stop recording it?
Yeah,